let us continue our isoparametric calculations. So, in the previous classes we had seen the different methods for determining the shape functions of isoparametric elements using the Lagrange method, and then the generalized coordinate method, and then also the serendipity method by progressive correction. And let us see, let us continue with what we had done. And before we do the calculations, let us see what is the requirement for convergence with the isoparametric elements. So, let the displacement field be expressed as A naught plus A1x plus A2y plus A3z. This is the general this is as per our generalized coordinate method, and this is particular for 3 dimensions, because you notice that we have 3 coordinates x, y and z, and at any point I, the displacement can be obtained by substituting xi, yi and zi, the coordinates corresponding to that point I, right. So, ui we can write like this: A naught plus A1 xi plus A2 yi plus A3 zi. Okay. And also in terms of the shape functions, the internal displacement field can be written as u is sigma of ni ui, where ni are the shape functions at different nodes and ui are the displacements at the different nodes. So, if you have 3 nodes in the element, we have n1, n2 and n3, and u1, u2, u3. Okay. And so, if you substitute 2 and 2 into 3 in terms of the shape functions, we get the displacement, internal displacement as A naught plus sigma ni plus A1 sigma ni xi plus A2 sigma ni yi plus A3 sigma ni zi. But our sigma of ni xi is actually x, that is the sum total of shape function value multiplied by the coordinate value is x, as we have seen earlier through the mapping functions. And you realize that in the isoparametric elements we use the same mapping and the shape function. So, this is true for our conventional systems. So, our u can be written as A naught times sigma ni plus A1x plus A2y plus A3z. So, but then this u is the same as what we had in the equation 1. So, if you compare this equation 5 with equation 1, that is, so in equation 1 we had u as A naught plus A1x plus A2y plus A3z. Okay. So, if you compare both of these equations, we have only sigma of ni as an additional term, and that should be equal to 1 for equation 5 to be equal to equation 1, because both are referring to the same displacement. So, we cannot have different values. So, that can be true only when the sum total of all the shape functions is equal to 1, and this is the necessary condition for convergence, and that is monotonic convergence. And we will also see or we will also perform some other test called as a patch test, that is referring to constant strain conditions to assure that whatever finite elements that we have developed, they do meet the requirements of the convergence. Okay. So, actually our sigma of ni of 1 is required so that we can simulate the rigid body displacements without straining the body, and also the constant strain state within the element. Okay. So, now let us see what or how we can do the calculations using the isoparametric elements. And as such, our finite element calculations are going to be too intensive, like we cannot obviously do by hand, and all these calculations are most ideal for computers because they are high speed computers, and then they can do the repeated calculations without any numerical mistakes. So, if you and I do, then every second calculation that we do, we might make a mistake, but a computer does not do these mistakes, and it can do very fast. Okay? And these isoparametric calculations are good for computer implementation because they are most ideal. It's a repeated calculations, and these elements are also applicable for any shape of element, whatever may be the shape in the Cartesian space, we convert to some standard shape in the natural space and do the calculations, and then we can choose the order of numerical integration based on the order of polynomial that we have. And the relation between our Cartesian system and then the isoparametric system is coming through our Jacobian matrix, as we had seen in the previous lecture, and we can express our derivatives of the shape functions in terms of xi and eta through the Jacobian matrix, and then the shape function derivatives with respect to the Cartesian coordinates x and y. And this term with these terms within the bracket, there we can think of them as mapping functions: dou x by dou xi, dou y by dou xi, dou x by dou eta, dou y by dou eta, and so this is j, and j is the is a very important parameter in our finite element calculations, and we call this as the Jacobian matrix. And the j inverse is 1 divided by determinant of the Jacobian matrix multiplied by dou y by dou eta minus dou y by dou xi minus dou x by dou eta, dou x by dou xi, and our determinant of this Jacobian matrix is this this cross product minus this cross product, and that represents the area of the element to some scale, and this will be positive only when the element nodes are numbered in the anti-clockwise direction. That is what we had seen even with the 3-node triangular elements. We numbered the nodes in the anti-clockwise direction to get the determinant of that coordinate matrix as positive, and it represents the area of the element to some scale. And the shape function derivatives with respect to Cartesian coordinates are this we have seen earlier, and so once we have these, we can form the B matrix and do all the calculations. And see, these Gauss-Legendre quadrature rules we have seen earlier, and in fact we had derived these sampling point locations and then the corresponding weight factors for the first 3 cases, 0.1, 2 and 3, and similarly we can also derive for 4-point numerical integration. And the main advantage this is we know exactly up to what order of polynomial they can exactly integrate. So, if you have 1-point integration, we can exactly integrate up to first order. 2 points means 2 times 2, that is 4 minus 1 is a third order polynomial. Similarly, 4 points means 7th order polynomial. And in general, once you have the element and then the type of problem, whether it is plane stress, plane strain or axis symmetric, and then whether it is a regular shaped rectangular element or a distorted element, we can estimate the order of polynomial that we will have, then accordingly we can choose the order of integration. And if you have a 4-node rectangle, the best order of integration is 2 by 2, and the maximum required order is 2 by 2, like we don't need more than that. And if it is a 4-node distorted, the best order is 2 by 2 and the maximum order is 3 by 3. Actually, the difference between these two is, see, theoretically you may require 3 points in each direction for exact integration of the quantities for estimating the stiffness matrix, but then when we are evaluating the stiffness of continuum, since we are considering only a finite number of degrees of freedom, we are overestimating the stiffness, and to partially compensate for that we use a lower order of integration. And so, and if you use a lower order of integration, we can partially compensate for the over stiffness of the continuum, then get better results. So, this that's the difference between the best integration order and then the maximum integration order. And by using the maximum integration order, you may not get any better solution, but definitely you will spend more computational effort. And if you have an 8-node quadrilateral like this, the best order is still 2 by 2, maximum order is 3 by 3. And if you have an 8-node distorted element, the best order is 3 by 3 and maximum order is 4 by 4. And let us look at the stiffness equation once again, and look at the steps required for doing the evaluation. Our stiffness matrix is calculated as this product B transpose dB integrated over the volume of the element, and in 2 dimensions we will do the integration in x and y. So, we have B transpose dB dx dy multiplied by thickness. In the case of plane stress and plane strain, we have the thickness, and in the case of axis symmetry we will have the radius. Okay. So, here it is put thickness or radius, that will give you the incremental volume. Okay. And we also know the relation between the Cartesian coordinates and then the natural coordinates. The dx dy is equal to a determinant of the Jacobian matrix multiplied by dxi d eta. So, we can write like this, this integral minus 1 to plus 1 minus 1 to plus 1 B transpose dB dxi d eta multiplied by the determinant of the Jacobian matrix. And in terms of summation, we can write this in this summation form, in the numerical form, by evaluating these quantities at different sampling points xi I and eta j, and then multiplying with the corresponding weight factors wi, wj, and then the determinant. And if you have an irregular shape or a distorted shape, the Jacobian value will not be constant. It might be varying at different sampling points. And so, these calculations are repeated several times. So, if you are using 2 by 2 integration in 2 dimensions, we are going to do this repeat the calculation 4 times, and then if you have a 3 by 3 integration, we will have 9 times, and so on. So, our B matrix has a size of 3 by 16 in the plane stress plane strain, because we have 3 strain components and then 16 degrees of freedom, and in the case of axis symmetric we have 4 strains. So, our K will be a 16 by 16 matrix for 8-node quadrilateral. So, these are the steps in our calculations. So at each integration point xi I, eta I, we need to get the shape function, and then we get the shape function derivatives with respect to xi and eta, and then we form the Jacobian matrix by determining dou x by dou xi, dou x by dou eta, and so on. And then we find the determinant of the Jacobian matrix, and then after that we can find the shape function derivatives with respect to x and y, or the Cartesian coordinates, and then we can write our B matrix in terms of the shape function derivatives, and this particular one is for plane stress and plane strain, dou n by dou x, dou n by dou y, and so on. And then we can form the stiffness matrix by this product B transpose dB, where B is our strain displacement matrix, D is our constitutive matrix relating the stress and strain, and this term we will see it in more detail when we look at the constitutive model in constitutive models. And then this is our determinant of the Jacobian matrix. So these calculations are repeated several times. See, for a 2 by 2 integration, we repeat these calculations 4 times, and we repeat this 9 times if we use a 3 by 3 integration. So almost double the times, and then if you use 4 by 4, it's even a larger number of times, 16 times. So actually it is most important that we do not use a higher order of integration than necessary. We should always go for the best order of integration, and as a general rule we use the least integration order. We do not use one point integration because it's mostly insufficient, and unless you have a 3 node triangle, for that we can use the 1 point integration, but for any general say 4 node quadrilateral or 8 node quadrilateral, the general thumb rule is use the lowest order of integration first, and then you also try with the higher order of integration, and then see whether the results are similar or not, so that we have confidence in the result that we get. And as I mentioned earlier, use of lower order of integration is better for us because we partially compensate for the over stiffness of the continuum. So now let us see the other calculations that is related to the estimation of the right hand side force vector, and the one of the terms on the right hand side is the body force vector, and that is written as n transpose B dV, and here I am going to illustrate only for a 4 node quadrilateral, so that I can write out all the matrices and vectors, and our PB is n transpose B dV integrated over the volume, and in terms of summation we can write like this: n transpose B Wi Wj, the determinant of the Jacobian matrix multiplied by thickness or radius, and our shape function matrix for a 4 node quadrilateral is like this: n1 0, n2 0, n3 0, n4 0, and so on, and our B is the body force vector, and it can have 2 components, one is in the x direction and the other is y direction, and that is simply rho gx, rho gy. Rho is the mass density, g is the gravitational constant, and our force vector has 8 components because we have 4 nodes, and at each node we have a component in the x direction and another component in the y direction. So we have 4 nodes, 1, 2, 3, 4. So this product can be written like this: double summation and then n transpose B Wi Wj, and then the determinant of the Jacobian matrix, and so on. And is actually, although we write like this, but inside a computer program we are going to evaluate each of these separately and then assemble them in a matrix form or in a vector form. So, do not be too confused by looking at this matrix. We are going to evaluate only term by term. And for an axisymmetric 4-node quadrilateral, we will have the radius. Okay? And this radius also could be varying with xi. So, when we estimate the polynomial order, we have to also look at the polynomial order that the radius could have. Okay? So, our equation will be like this. Everything is the same except here we have the radius evaluated at xi I and eta j. And so the N matrix is a first order polynomial for the 4-node quadrilateral, and if our element is rectangular, the j is constant. So, the calculation for the force vector is only a first order polynomial, and one point integration is sufficient, that is for plane stress and plane strain. But for axisymmetric problems, the radius r is a linear polynomial because it is varying with the xi and eta. So, our product will be a second order polynomial. So, we need a higher order of integration. Okay? And if element is distorted, j could be of first order, that we will see with examples, numerical examples, and then accordingly our order of polynomial will change. Okay? And for 8 and 9 node quadrilateral, our shape function will be of second order, and our j will also be having second order terms. Okay? Let us calculate the body force vector for a rectangular plane strain element. And as you recall, the plane strain element has unit thickness in the outer plane direction, right? And this element has 4 nodes: node 1, node 2, node 3 and node 4. And please note that all these 4 nodes are numbered in the anti-clockwise direction, and these are the coordinates. Node 1 has coordinates 20 and 15, node 2 8 and 15, node 3 8 and 7, node 4 20 and 7, and we can evaluate the shape function values at different integration points, and also we need to calculate our determinant of the Jacobian matrix. So, these are the 4 shape functions, and these are the derivatives of the shape functions with respect to xi and eta, and dou x by dou xi is the summation of dou n by dou xi times xi, and if you substitute the dou n by dou xi and then the different coordinate values, we will see that dou x by dou xi is 6 and it is constant, it is not varying with xi, and dou x by dou eta we will see that it is 0, and dou y by dou xi is also 0, and dou y by dou eta is 4. So, actually if you see the x and y coordinates are coinciding with the xi and eta coordinates. They are parallel to each other, or they are just coinciding because we can literally move the location of these coordinates, and because they are parallel to each other, as you are moving along xi, your y is remaining constant because our element shape is rectangular. So, our xi and eta they are going to be oriented towards the length and height of the element, and as you are moving along eta, your x is going to remain constant, So our dou x by dou eta is 0, and as you are moving along xi, y is constant, so dou y by dou xi is 0, and then dou x by dou xi is 6 and dou y by dou eta is 4, and we can see, you can relate them to the length of the element. Length of the element is 20 minus 8 is 12, and the height is 15 minus 7 is 8, and 12 is the length, and divided by 2 is your dou x by dou xi, and the height is 8, and dou y by dou eta is 4, 8 by 2. Okay, and our determinant of the Jacobian matrix is 24, and our area of the element is 12 times 8, that is 96, and our Jacobian determinant is 24. So we see that the determinant of the Jacobian matrix is A by 4, 96 by 4. Okay. And our force vector P is the summation over xi and eta n transpose B times determinant of the Jacobian matrix, then Wi Wj times thickness. And for this case, because we have a first order polynomial, we can just use one point integration, and at one point integration xi and eta are 0. So if you substitute xi and eta of 0, we get 1/4 for all the shape functions. So you have this n transpose as 1/4 0 0 1/4 and so on, and our body force vector, our unit weight is 20, and if you take the y axis as vertical upwards, the gravity is going to act downwards, so it is minus 20, 0 and minus 20, and the determinant of the Jacobian matrix is 24, and the weight factors are 2 and 2, thickness is 1. So it is so we see this the force is equally distributed between all the nodes, all the 4 nodes, minus 480, minus 480, minus 480, minus 480. Okay. And the thickness for the plane strain element is 1, that is what we used here. Okay. And now let us do the same calculations for axisymmetric element. Let us take the same dimensions, the same coordinates, except that now we have an axisymmetric geometry, and so the volume of this element for a unit radian is 1344, and then the weight of the element is the volume multiplied by 20, that is 26,880, and this weight is per unit radian. As we have discussed earlier, the 2 pi is common both on the left hand side and the right hand side, so the 2 pi gets cancelled out, and we work only in terms of unit radian. Okay. And so if you use a one point integration for the axisymmetric problem, and our radius at xi and eta of 0, that is at the center point, will be the average radius. 20 plus 8 is 28, by 2 is 14, right? And so the entire thing is the same as we had seen for the plane strain case, except for the radius here. So now our force is 6720, equally distributed at all the 4 nodes, and we can realize that this is not correct, because our order of polynomial is 2. So our order of polynomial in the shape functions is 1, and then for the radius is 1. So the total order of polynomial is 2. So that means that you need minimum 2 point integration for getting a good result. So so this distribution is not consistent with the type of element. But then if you look at the total weight, 6720 times 4 will give you the same weight as 26,880. at least we are able to calculate the exact total weight, because our area is actually it's a first order polynomial, and we can evaluate the area exactly. Okay, and so we need to go in for higher order integration, and this is and this result is obtained with 2-point integration, 2/2 integration. And now you see that the distribution of loads has changed between the nodes. On the two outer nodes we have a force of 7680, whereas in the inner nodes we have 5760, and if you total up all these loads, it will add up to 26,880. Okay, that you can easily see, and this is with a 2/2 integration. I will show a computer program that you can utilize, or otherwise we do the previous calculation 4 times and then add them up. Okay, and the same problem with slightly different coordinates. Here we have the axisymmetric element starting from the origin. Okay, and now our total weight is 32,000, and the distribution is like this: 10,666 on the outer nodes, and inside nodes 5,333, and the sum total of all these 4 forces will be equal to 32,000. And what we are doing within the axisymmetric element is we are doing the calculations only for unit radian. We are not doing for the full 2 pi. Okay, and this is what we are doing, like this is the volume that we are dealing with. Okay, and some questions for you to think about. See, what is the reason for difference the loads at outer and inner nodes in the axisymmetric element? See, this is what I mean. See that the outer node we have 10,666, whereas in the inner node we have 5,333. In this case it is exactly 2 times the difference, like 2 times of this is this, but in the previous case it is not 2 times, it is some value 5,760, and the outer node is 7,680. See, this distribution depends on the geometry, and I want you to think about and answer what is the reason for difference, and then can you derive a relation for the ratio of the loads in terms of R2 and R1, in terms of the loads at the outer node and the inner node. Anyway, through the finite element calculations we get the exact loads, but whether you can think differently and get some analytical equation in terms of R2 and R1, you please try them out and you can send me the solutions. So now let us do the same calculation for a distorted element, a plane strain distorted element. Our coordinates are like this, and with the 2/2 integration these are the loads at different nodes, and if we use 1-point integration we get the load of 312.5 at each of these 4 points. So adding up to a total of 1250, but then the nature of distribution is different. Okay, this is with 2-point integration. This is the result from the program that you are going to see later. This is node 1, node 2, node 3, node 4. These are the forces that are estimated using 2/2 integration. And now let us look at the axisymmetric element, the same element but in the axisymmetric geometry. And so with 1-point integration we get the same load at all the 4 nodes, and with 2 by 2 integration we get a different distribution at node 1, node 2, node 3, node 4. Okay. And even with 3 by 3 integration we get the same loads. Say at node 1 with the 3 by 3 integration 3398, and even with the 2-point integration it is the same 3398. So that means that with the 2-point integration itself we can get the accurate result, and if you use a higher order of integration you are only going to spend extra time, but then you will not get any different result. I will show you this program a bit later. Okay. And now let us look at the 8 node quadrilateral element. Okay. And this is 8 nodes 1, 2, 3, 4, 5, 6, 7, 8. So when we have higher order elements we always number the corner nodes first, because the corner nodes are the minimum required for defining any quadrilateral elements, and then inside we can define the mid-side nodes like 5, 6, 7, 8 or only some of them. Okay. And see this n transpose B calculation is done for a 4 node element, and our gravity force is acting down, but then you see at these 4 corner nodes you see the force going up, whereas at the 4 this mid-side nodes the force is going down 640, and of course the total of all the 8 nodes adds up to the total weight of the element 1920. And but if you get this type of result we should not be thinking that it's wrong, because it's we call it as a consistent distribution of loads n transpose B integrated over the full volume, and if you are not convinced whether this is correct or not, you can go for higher order of integration and check whether you get any different result. And actually this distribution is consistent with the way the stiffness of the element is distributed between the different nodes. Okay. And here is the distribution for a 9 node quadrilateral. Is actually previously we had seen for 8 nodes, now we have for the 9 nodes. And when we have the 9th node, you see all the loads are pointing downwards. Previously with the 8 node element we had seen at the corner nodes the load is acting up, and you see the difference between the load at the corner nodes and then the mid-side node. It is 213.33 by 53.33, that is 4 times, and then 4 times of this load is distributed to the center point, the center of the element, and compared to the corner points this is 16 times. Actually we can see based on this the center point has more weight in terms of the stiffness, like these degrees of freedom at this node, at this 9th node will have much higher stiffness contribution, and correspondingly we also get higher load when we distribute this n transpose B dV. Okay. And till now we have seen this n transpose B calculations, and now let us do this B transpose sigma calculation, because this is a very important calculation, because in all our finite element analysis in geotechnical engineering we will be doing this not only for checking for the equilibrium of the system, but also for modeling construction and excavation, and then the pre-stressing and so on. And let us do for a rectangular element like this, and the coordinates the length is 10 and the height is 5, and these are the coordinates, and then the 4 nodes 1, 2, 3, 4, and once again we have an anti-symmetric, sorry, the numbering is in the anti-clockwise direction 1, 2, 3, 4. Okay. And the B matrix is a linear polynomial in xi and eta, and the J matrix is a constant matrix due to the rectangular shape, because we have seen with the rectangular shape earlier that dou x by dou xi is constant, and that is equal to length divided by 2, dou x by dou eta is 0, and dou y by dou eta is 0, and dou y by dou eta is half of the height. Okay. So, our determinant of the Jacobian matrix J is A by 4, that is 12.5, and dou y by dou eta is 5 by 2, and dou x by dou xi is 10 by 2, and we can calculate dou n by dou x and dou n by dou y through our equations that we derived earlier. And if you assume constant stress state, we can just simply use a one-point integration, because our B matrix is a linear polynomial. Okay. And at xi and eta of 0, that is for one-point integration, our dou n by dou x at different points is like this, and the dou n by dou y at different points is like this. This we have 3 rows because we have 3 strains, and then 8 columns because 8 degrees of freedom. And let us say that our sigma x is minus 50, sigma y is minus 100, and tau xy is 0 and everywhere. And so our sigma in the vector form is minus 50, minus 100 and 0, and our B transpose sigma will have number of rows of 8 and columns 1, that we can easily see from here, 8 by 3 multiplying 3 by 1, that is an 8 by 1 vector. And if you go through this full calculation, you will get a force vector like this, and we can plot them on the element like this. This minus 125 at node 1 is in the negative x direction, and minus 500 is in the negative y direction at node 1 like this, and at node 2 it is positive 125 and then negative 500. At node 3 both x and y are positive. At node 4 x is a negative force and y is a positive force. Okay. So, here we see that the equilibrium is satisfied, like there is whatever force that you have downwards is also the same force acting up, and then from the sides also we have. So, that means that at the element level we have perfect equilibrium, and then the sigma x is the net lateral force divided by the height multiplied by 1. Okay. So, that is 125 plus 125 by 5, that is 50 compressive. Then sigma yy is 500 plus 500 divided by 10, that is 100 compressive, that is that is what we had specified. And then there is no shear stress, because along any surface there is no shear force, 125 and minus 125. So, it is they compensate each other. And let us consider a pure shear stress. Let us apply a shear stress of 100, and if you do the calculation, the force distribution is like this. So, at node 1 500, 250, node 2 500, 250 going down, and node 3 it is minus 500 and minus 250, node 4 minus 500 and plus 250. Okay. And the shear stress along any surface, say along this horizontal surface we have 500 plus 500, that is 1000 divided by 10 times 1, that is 100, and then on the vertical face 250 plus 250 by 5 times 1, that is 100. So, that is the applied shear stress, and we get the same shear stress even by manual calculation. And so actually this is our sign convention. So any clockwise, if any shear force develops a clockwise moment around an interior point, we call that as a positive shear force, and this is the positive shear stress, positive shear force and positive shear stress. Okay. And so the load vector for the same stress state on an 8-node quadrilateral is like this. It's a bit more complicated, because at the mid-side node we have 4 times of the load at the corner nodes, whether it is in the vertical direction or the lateral direction. 166.66 multiplied by 4 is this, 41.66 times 4 is this 166. And if you look at the 9-node element, interestingly there is no force here. That is understandable, because that is the point of center of gravity, and for maintaining symmetry the forces at the center of gravity should be 0, because there are no deformations if that is the center of that's the symmetry plane. Okay. And for doing these calculations, I am going to show you one computer program, very simple computer program that you can run, because see, for a 4-node quadrilateral we can do hand calculations, but not for 8 and 9 node, because the number of terms is more. So if you have any questions, please write an email to this address, profkrg@gmail.com, and I will reply back. So thank you very much.